Today we will talk about the role the brain plays on motor rehabilitation and the processes it undergoes to allow for motor learning to take place. Every time we do something, the activity is initiated and regulated by the brain, whether it's voluntary or not. When we want to learn a new skill, such as speaking a new language, learning how to solve a math problem, taking up a new sport, or even doing whatever this is, our brains are instrumental in the learning process. In order for us to add an activity to our repertoire, the brain must store this information so that it becomes reproducible. This is done through a process called neuroplasticity. During neuroplasticity, the brain circuitry gets rewired by the addition of new synaptic connections and/or the strengthening of existing ones, as well as reorganization of the cortical representation of the body parts involved in the activity to be learned. Nonetheless, we don't acquire a new skill after performing it once. Neuroplasticity takes time, and it requires a lot of repetition in order for the information to imprint on the brain. Motor disabilities can originate on the effector organ that ends up being impaired, or they can result as a consequence of a neurological disorder, such as a stroke. In either case, neuroplasticity takes place in the motor cortex when the brain adapts to the reduced motor capabilities. In physical rehabilitation, the relearning of a motor skill is interpreted by the brain as a completely new skill. Naturally then, the process of neuroplasticity is involved in motor rehabilitation. All of this makes us wonder, what if we could find a way to prime our brains for neuroplasticity and therefore facilitate the process of learning a new motor skill? Studies have been carried out to do precisely that, and fortunately, a few techniques have been identified. In one approach, assistive hybrid robotics utilizes an external exoskeleton to aid the patient with the motor task while simultaneously providing the muscles involved with an electrical stimulus to compensate for the reduced signals coming from the brain. A second technique involves cortical stimulation, in which the region believed to be responsible for the deficient movement is also provided with an electrical stimulus to help the synapses reach threshold activation levels and therefore promote neuroplasticity. Motor imagery is a form of implicit motor learning where the subject visualizes the task and is deprived of a conscious awareness of motion. Additionally, aerobic exercise has been shown to increase the amount of neurotrophic factor present in the brain, a protein that is believed to be associated with neurogenesis and neuroplasticity. Therefore, aerobic exercise could serve as a primer for the acquisition of new skills. Lastly, the use of real-time functional MRI has been implemented as a way to provide patients with real-time neurofeedback from their own brains and help them to self-regulate their neuronal activity without any physical exertion. Some of these approaches can be really useful for patients who have limited range of motion or who experience physical pain, offering them an alternative and faster route towards motor recovery. All of the proposed techniques make us feel hopeful about the future. Perhaps one day, we will be able to personalize treatments, design medical devices that accelerate the rehabilitation process, and who knows, maybe even successfully insert the necessary neurons into the affected regions of the brain and bring about controlled synaptogenesis. Thank you so much for listening.